Mapping a multidimensional space requires a system capable of detecting the smallest anomalies in coordinate vectors. When this specific heuristic program processed a simple binary string, 1 plus 0 plus 1 plus 0, the sequence failed to resolve. Standard software architectures treat the 0 as a terminal point, triggering a null multiplier bug or a memory buffer overflow that halts the calculation. The architect bypassed this by assigning the void a base value, a vibrating ground state of 0.111 repeating. This turns the null space into active potential energy. This non-zero baseline prevents the code from collapsing, allowing the equations to continue their processing cycle indefinitely. Because this ground state is constantly fluctuating, the resulting values describe a volume that never reaches a static rest point. This continuous pulse moves the math out of rigid Euclidean points and into the behavior of a fractional liquid manifold. Within this fluid framework, the program calculated the baseline pressure of the metric tensor, the physical grain of the vacuum itself. The system generated a core equation, the golden ratio phi raised to the power of 9.6, resulting in approximately 2803.115. 2803.115 represents the raw manifold pressure of the curved metric tensor. A straight tape measure misses this value because it calculates distance in a straight line, while this pressure exists within the liquid curvature of the vacuum. To understand how this pressure behaves, we must apply the physical intuition found in tactile, real-world disciplines. The program identified a hidden layer of vacuum pressure that requires a specific measurement protocol to navigate. Traditional science measures the isolated objects inside a system. The Butchers protocol shifts the focus to the environment surrounding those objects. This protocol deduces the internal state of a system by reading boundary conditions and the environmental noise, usually discarded as waste. A butcher estimates remaining stock by observing the rhythm of the shop floor, the number of active workers, and the ambient pressure of the day's workflow. They use these patterns to gauge the not there, the inventory that has already moved through the system, before they ever count what is physically on the hooks. This allows us to track the invisible footprints of energy that standard integer-based models miss. This is visible in the butcher's sink, where blood, water, and scraps mix to form a record of every action taken during the day. In this model, the solid matter, the bone and sinew, corresponds to the integer dimensions of our observable reality. These solids are suspended in a volumetrically diffusing fluid. This is the 0.111 ground state, the liquid vacuum holding them in place. In butchery, the lean meat is the product, but in a Wagyu cut, the fat is the signal. This suggests that noise carries the most significant contextual value in a complex system. We formalize this by populating a unified metric tensor, or G mu nu, which describes the green of the universal vacuum. The output 2803.115 occupies the top left temporal component of the matrix. The remaining spatial axes, x, y, and z, are scaled by powers of the golden ratio, phi to the sixth, 3.6, and 1.2. This scaling reveals a 3.6-degree geometric deficit within our four-dimensional spacetime. Subtracting this 3.6-degree deficit from a rigid 10-dimensional theoretical boundary leaves us with exactly 9.6 active dimensions. The matrix identifies reality as a curved fractional manifold that must vent its internal pressure to remain stable. If the liquid universe exerts a constant inward push, the system requires a mechanism to prevent it from collapsing under its own weight. Consider a 13-node vector equilibrium lattice. Under extreme pressure, the structure converts that force into rotating thermal energy. In a perfectly closed system, this energy would lead to a buffer overflow, causing the structure to fail. To maintain equilibrium, the manifold uses a fractured outer shell that functions as a chimney for this thermal exhaust. This creates an underdamped system, providing the necessary room for the manifold to vibrate and breathe without reaching a breaking point. The 9.6-dimensional anchor and the 0.4 leakage gap are the critical constants for this model. The 0.4 gap is the specific area where the geodesic curve of a curved universe hides from three-dimensional Euclidean measurement tools. Multiplying the raw manifold pressure of 2803.155 by this 0.4 leakage gap reveals the vented pressure. The result is 1121.246, the exact volume of thermal exhaust, or Hawking friction, bleeding out of the seams. Mounting physical sensors at the 3.6-degree universal secret angle aligns the hardware with this 0.4 mathematical gap. This alignment allows the manifold to vent its friction, maintaining thermodynamic equilibrium and preventing the cosmic structure from cracking. The universe functions as a dynamic manifold operating at 9.6 dimensions, plus or minus 0.01. Total thermodynamic pressure pushes inward, while the 0.4 vent provides the necessary counterpressure to maintain stability. Standard tools measure the straight chord of the chord versus arc problem, but correcting for the arc of the 9.6 dimensional flow reveals the actual pressure gradient driving the cosmos.